All right, let's take a look at a problem, a popular problem in many physics books, which is the problem of a leaning board. So the problem has a plank or a board or a ladder that is leaning against the wall, is on the floor and leaning against the wall. Um, there is friction between the board and the floor, described by a coefficient of static friction mu sub s. There is no friction between the board and the wall, so that those two surfaces have a mu sub s equal to 0. The board has a length L. It is a uniform board, so that means that the center of mass is located in the middle of the board, and the angle at which the board is leaning against the wall is theta, as measured from the floor. So this is the situation, and the problem that we're trying to solve, the question that we're trying to solve, is what's the minimum angle theta before the plank starts to slide. So clearly when we start with the plank pretty close to the vertical, the plank is barely touching the wall, is barely leaning against the wall, and that's it's a very stable situation. But as we decrease the angle at which the plank is, or the board is, leaning against the wall, eventually you'll notice, if you do this experiment, very simple to do with a ruler or some kind of board or plank, you'll notice that when the angle gets small enough, the plank starts to slide. Okay, so we would like to find at what angle would the plank starts to slide. Okay, so that is the setup of the problem. So let's take a look at the forces. So for a plank that is leaning against the wall is supposed to be vertical. We're going to have the normal that the wall is going to put on the top of the plank. So since the wall is vertical, this force is going to be horizontal. Remember that normal forces are always perpendicular to the surface. We also have another normal, which is the normal between the plank and the floor. This is perpendicular to the floor, pointing up. We do have friction at the bottom, so the force of static friction, we're assuming the plank is not sliding, so this is static friction force, and the bottom of the plank wants to slide to the right, so the force of static friction should be to the left. The plank has a mass, so the plank must have weight, and the weight vector, we're going to attach it to the center of mass, which, as we said before, is a uniform plank. It's supposed to be in the middle of the plank. So these are all the forces that are affecting the motion of the plank, which is the object of interest in this problem. So the other parameter that we want to set up here is the angle theta, that, as I said, is the angle between the plank and the floor. Now, we are interested in looking at the equations that apply for a plank that is not moving. So what that means is that we're dealing with a static equilibrium problem. In a static equilibrium problem, because of the absence of motion, the acceleration in the x direction is 0, the acceleration in the y direction is also 0, and the angular acceleration, alpha, is also equal to 0. So the problem is in a rotationally in equilibrium, and also linear motion is also in equilibrium. So when the acceleration in the x direction is equal to 0, the sum of the forces, according to Newton's second law, must be also equal to 0. So looking at our forces and the directions that they have, we notice that there's only two forces in the x direction, so that is Nw to the right and the force of static friction to the left. So Nw minus Fs equals 0. And we get our first equation that tells us that the force of the wall, the normal with the wall, is equal to the force of static friction. Our second equation is going to exploit the fact that the acceleration in the vertical direction of the plank is also 0. So if that's the case, all the forces in the vertical direction must cancel, and the forces that we have in the vertical direction is the normal with the floor, positive, and the weight of the plank, negative. So that gives us that Nf minus Mg is equal to 0, and we have our second equation for this problem, which is the normal with the floor equals the weight of the plank. So far we have used the two linear accelerations being equal to 0, therefore the sum of the forces equal to 0. Now, rotationally speaking, since the angular acceleration is 0, the torques must cancel. The sum of the torques must be equal to 0. Remember that this is with respect to any point. So it is up to you to choose what you call the pivot point in the problem. So what we're going to do is choose the pivot point to be at the bottom of the plank. The reason we do that is because if we do that, then the torque of the normal with the floor would cancel, because any force applied to the pivot has zero torque, and the torque due to the force of static friction would also cancel. We do not have to calculate these torques because they are directly equal to zero. So that is a good simplification. So we're going to choose that as the pivot point. So with that pivot point, as we said, the torque of NF is 0. The torque of the force of static friction is also 0. Now we need to evaluate the torque of the force of gravity. The force of gravity is this force, and it has a torque. The torque is equal to the magnitude of the force of gravity multiplied by its moment arm. That is the perpendicular distance between the line of the force, right here, and the axis of rotation, the pivot. The distance, as you can see, is L divided by 2 times the cosine of theta. L divided by 2 is the hypotenuse of the small triangle, right here, L divided by 2, and multiplied by cosine gives you the horizontal distance. That is the moment arm of the force of gravity. So with that, we can write the torque of the force of gravity as mg. It's a positive torque because it's counterclockwise, and mg times L over 2 cosine theta. That's the torque of gravity. And we have one more torque to go. That's the torque due to the normal with the wall. So this force is going to do a torque in this direction with respect to the pivot. The magnitude of that torque is going to be minus the it's a negative torque because it's clockwise, so it's going to be NW times L, but we need the moment arm. L is not the moment arm. The moment arm, meaning the distance between the line of the force and the axis of rotation, this distance as indicated here is L sine theta. So the torque for the normal with the wall is going to be negative NW times L sine theta. This distance right here is the moment arm of NW. The D, that's the letter that we've used for moment arm, the moment arm of the force normal with the wall. So the sum of these two torques is equal to 0, and therefore we get our third equation, which tells us that the, let's take a look at that equation right here, NW, the normal with the wall, times L sine theta equals mg L over 2 cosine theta. We can cancel an L and write that the normal with the wall should be equal to mg cosine theta divided by 2 sine theta. So at this point we have three equations that we have derived. The equation for the normal with the wall, which first equation says that it should be equal to the force of static friction. Those two forces cancel out. Second equation says that the normal with the floor should cancel the weight. And the third equation was due to the torques. The torque of the normal with the wall should be cancelled by the torque of the force of gravity. Now, to understand why there should be a minimum angle at which the plank starts to slide, let's take a look at how are the behavior of NW with respect to theta. So let's start with a theta of 90 degrees. So suppose that we have the plank that is balanced at its bottom end, the angle is 90 degrees. So basically the plank is really not leaning against the wall. So our equation clearly says that, which is it gives us a normal with the wall equal to 0. The plank is not pressing against the wall, so the wall does not do or apply any force to the plank. Notice that our equation gives us NW equals 0 because the cosine of theta when theta is 90 degrees gives us 0. The sine of 90 is 1, so the numerator is 0. The denominator is 2, so the normal with the wall is equal to 0, which is, again, what you would expect. Because the normal with the wall is equal to 0, equation number 1 tells us that the force of static friction would also be 0. If the normal with the wall is 0, there is no need for static friction at the bottom. The bottom of the plank is not trying to slide left or right. It's just the plank is balanced at the bottom. So that makes sense. And the second equation, number 2, tells us that the weight of the plank is equal to the normal with the floor. So those two forces, the only two vertical forces in the problem, cancel each other out. Okay, so that's clear, I hope. Now let's take a look at what happens when the angle is not 90 degrees. Let's suppose that we start leaning the plank. We grab the plank and we lean it against the wall, not at 90 degrees, but start at 89 degrees, 88, 87, etc. We start decreasing the angle, and we want to see what the equations tells us about, for example, the normal with the wall. So if you take a look at the equation, from that equation we see that the normal with the wall is going to grow from 0 at theta equals 90 degrees to a greater value, positive value, as theta decreases. Take a look at that. Should be the case because the cosine of theta right here is going to grow as theta decreases from 90 degrees. At 90 degrees the cosine is 0, but as theta decreases the cosine is growing, the numerator of this fraction is growing, and the denominator is decreasing because the sine of 90 is 1, and when you decrease the angle from 90 the sine starts to come down from 1. So the denominator of this fraction is decreasing, the numerator is increasing. So what that tells you is that the normal with the wall is definitely growing as we decrease the angle. Since the normal with the wall is increasing as we decrease theta, notice that that means that the force of static friction has to grow also. That's because of equation number 1. Equation number 1 says, right here, says that the normal with the wall equals the force of static friction. So as the normal with the wall grows, then the force of static friction has to grow also. But if the force of static friction, as we decrease the angle, the force of static friction down here grows and grows and grows, eventually what's going to happen? What's going to happen is that the force of static friction will reach its maximum value. The maximum value that the force of static friction can reach is mu sub s times the normal. So at an angle theta, eventually the force of static friction becomes equal to mu sub s times the normal with the floor. The normal with the floor is mg. The normal with the floor is mg, so we can replace normal with the floor equals mg, and we get that the equation says nw equals F sub s, which is equal to mu sub s times mg. So writing those two results, we get the following equation. Let's erase here some of this stuff that I did before. And what this says is maximum force of static friction is equal to mu sub s times the normal is mg, and that should be equal to nw from equation number 1. But nw we got it from here, from the equation inside the orange square. That's mg cosine theta divided by 2 sine theta. So let's put those two things together, and we have mu sub s times mg, which is F sub s, equals mg cosine theta over 2 sine theta. This is F sub s equals nw. So we can cancel m and g and solve for sine theta divided by cosine theta, moving the sine theta to the numerator on the left, cosine theta in the denominator, and we can finally write our expression more compactly as tangent theta equals 1 over 2 mu sub s. Okay, so this equation answers the question, what is the minimum angle at which you can lean the plank before the plank starts to slide? The answer is that the only parameter that determines that angle is the friction between the plank and the floor, the coefficient of static friction between the plank and the floor. This is the only parameter. The mass of the plank did not matter, the length of the plank did not matter, as long as as soon as we reach this value for theta, the plank will start to slide. All right, I hope that helps, and I'll see you in the next one.